Today, today we shall study about basic transistors configuration and transistor characteristics. In transistor, only three terminals are available, which are emitter, base and collector. Therefore, in a circuit, the input-output connections have to be such that one of these is common to both the input and output. Accordingly, the transistor can be connected in either of the following three configurations: common emitter, common base, common collector. The transistor is most widely used in the common emitter configurations, and we shall restrict our discussion to only this configuration, since more commonly used transistors are NP and Si transistor. Common emitter transistor characteristics: when a transistor is used in common emitter configuration, the input is between the base and the emitter, and the output is between the collector and the emitter. The variation of the base current is IB, with the base emitter voltage VB is called the input characteristics. Similarly, the variation of the collector IC with the collector emitter voltage VC is called the output characteristics. The collector current changes with the base current. The input and output characteristics of a NPN transistor can be studied by using the circuit. To study the input characteristics of the transistor in C configuration, a curve is plotted between the base current IB against the base emitter voltage VB. The collector emitter voltage is kept fixed. While studying the dependence of IB on VB, we are interested to obtain the input characteristic when the transistor is in active state. So, the collector emitter voltage VC is kept large enough to make the base collector junction reverse biased. Since VC or VCB plus VB, and for SI transistor VB is 0.6 to 0.7 volt, VCE must be sufficiently larger than 0.7 volt. Since the transistor is opened as an amplifier over a large range of VC, the reverse bias across the base collector junction is high most of the time. Therefore, the input characteristics may be obtained for VCE somewhere in the range of 3 volt. In the range of 3 volt. Since the increase in BC appears as increase in BCB, the effect on IB is negligible. As a consequence, input characteristics for various value of VC will give almost identical curves. Hence, it is enough to determine only one input characteristics. The input characteristics is as shown in figure 2A. The output characteristics is obtained by observing the variation of IC as VC is varied, keeping IB constant. It is obvious that if VB is increased by a small amount, both whole current from the emitter region and the collector and the electron current from the base region will increase. As a consequence, both IB and IC will increase proportionality. This shows that when IB increases, IC also increases. The plot of IC versus IBCE for different fixed values of IB gives one output characteristic. So there will be different output characteristics corresponding to different values of IB as shown in figure 2B. The linear segments of both the input and output characteristics can be used to calculate some important AC parameters of transistors as shown below. Input resistance: this is defined as the ratio of change in base emitter voltage to the resulting change in base current delta IB. At constant collector emitter voltage VC, This is dynamic AC resistance and bias can be seen from the input characteristic. Its value varies with the operating current in the transistor. Ri बराबर delta VV बटा delta IV and VC बराबर constant. The value of Ri can be anything from a few hundred to a few hundred ohms. Output resistance RO. This is defined as the ratio of change in the collector emitter voltage delta VCE to the change in collector current delta IC at a constant base current IB. RB बराबर delta VCE बटा delta IC at IB बराबर constant. The output characteristics show that initially for very small value of VC, IC increases almost linearly. This happens because the base collector junction is not reverse biased and the transistor is not in active state. In fact, the transistor is in the saturation state and the current is controlled by the supply voltage DC. In this part of characteristics, when BC is more than required to reverse bias the base collector junction, IC increases very little with VC. The reciprocal of the slope of the linear part of the output characteristic gives the value of RO. The output resistance of the transistor is mainly controlled by the bias of the base collector junction. The high magnitude of the output resistance is due to reverse bias state of this diode. This also explains why the resistance at the initial part of the characteristic when the transistor is in the saturation state is very low. Third, current amplification factor B beta. This is defined as the ratio of the change in collector current to the change in base current at a constant collector emitter voltage VC when the transistor is in the active state. Beta AC बराबर delta IC बटा delta IV at VC बराबर constant. This is also known as a small signal current gain and its value is very large. If we simply find the ratio of IC and IV, we get what is called DC beta of the transistor. Hence, beta DC बराबर IC बटा IV. Hence, IC increases with IV almost linearly and IC बराबर 0 when IV बराबर 0. The values of both and nearly equal. So, for most calculation, beta DC can be used. Both the beta BC and beta DC vary with BC and IV or IC slightly.